Okie dokie, in this video we're going to talk about how I can take an existing graph and just performing some transformations on it. So the first one we're going to do is let's pretend this blue graph, and I'll write that in blue here. The blue graph is f of x, and we're going to draw in purple. In purple we are going to draw, actually I think I used red in class, so I think we're going to use red. In red we're going to graph q of x, and that's going to be 1/2 times f of x. And then in purple, we're going to graph h of x, which is f of 2x. And the reason we're doing this video is just to show you that I can actually use a table to also help me out, in case I forget what actually happens. So we know, kind of just from the previous videos, that what this effectively does is you take f of x and you smush it with a factor of 1/2. Factor of 1/2. In other words, it's going to be half as tall. But here's how we can kind of use a table to, in case I forget. Because when you're taking a test, you get pressured and you just kind of freak out a little bit. Happens, I get it. So let's evaluate x here, and I'll plug in f of x. And then I'm going to evaluate q of x, and we'll see why. So I have these 4 reference points, so I'll just start with those. I have -4, I have -2. For the heck of it, we'll just put in 0 as well, because 0 is always nice. And then we'll plug in x equals 2 and 4. So just from this blue graph here, we know what f of x is. Actually, I'm going to keep that in blue, so we'll use blue here. F of x. So we know when I plug in -4, I get -2, -2, 0, 2, and then -2 again. I guess that's one problem with this graph, is that it uses -2 a lot. But anyway, so if I want to find what q of x is, well, q of x is defined to just be f of x divided by 2. And so really this is just equal to f of x, which was -2, so I'm going to write that right here, times 1/2, which would be just -1. And if I want to evaluate q of -2, I just need to take f of -2. So again, this right here, that is f of that's f of -4, that one right there. And so now I just need to find half of f of -2, which is essentially 1/2 times -2 again, which is -1, and so on. And so the rest of these, again, you're just taking the original y coordinate and multiplying it by 1/2. And so if I were to fill the rest of this out, this would be 0 still, 1, and then -1. So here's where all these reference points go. These ones that are underneath the x-axis, I also wanted to bring up this point, is that when we're doing a stretch or compression, you treat kind of the axes as the center. And so what I mean by that is when we're doing a vertical compression, all the points that are below the x-axis are moved closer to the x-axis, and any point on top is moving down closer to it. And so this point right here, -4, -2, now becomes, on q of x, -4, -1. And likewise, so I can have all these points, just move my reference points here. And the reason it's helpful to have the reference points is because when we do these transformations, the general shape of the graph is not changing. So it's not like you're going to have part of the graph. So this graph consists of a bunch of straight line segments. It's not suddenly going to be curved or anything like that. So we can just move those reference points and connect them like so. So this red graph here is what q of x would look like if q of x is 1/2 times f of x. Okay, so now let's move on to h of x. And so this is going to be, I'm going to have to clear this up a little bit. Let me make some room. So h of x, remember from our transformations and just kind of how they do what they do, we know that this one is going to be a horizontal compression. And this time you're getting pushed in half as wide. It's going to be half as wide. And here's a way that we can model this with a table. Okay, so what I've done here now to see this purple graph h of x, which is a horizontal compression of f of x, is I've started off with this table by just reminding us what f is evaluated at -4, -2, 0, 2, and 4. So now let us evaluate h of x at each of those inputs. So when I plug in, or when I check h of -4, well, based on the rule here, this would say that it's really the same thing as f of 2 times -4, which would be -8. So in this case, that's actually not defined because the graph -8 is not in the domain of this f. So that won't matter right there, which would mean now that h's domain is not from -4 all the way to 4. It's going to be different. And we'll see how it's different. And we know it's going to be actually half as wide as the previous one. Now, if I evaluate h of -2, well, let's see, that'd be f of 2 times -2. So that would be equal to f of -4. And hey, f of -4 is actually right there. So that is just going to be equal to -2. And so I'll plot that point here on the original graph, or overlay it on the original graph. So this point right here, sorry, make it really big for you, that -4, -2, when I move it, is now going to be right here. Okay, let's keep going. Now if I plug in h of 0, well, that's just going to be f of, well, 2 times 0 is still 0. And so that will still be an output of 0. Continuing on, h of 2 is really asking for f of 2 times 2, or 4. And so you can see what's happening is that each each point on h has the same y value as the input of f that was twice as large. And so essentially h is taking all of those points from f and bringing them, and they're happening at x values that are half as large. So that's why it gets squished inward as opposed to stretched outward. I wish that I had my video on now because I'm doing stuff with my hands. That helps, I think. Anyway, so this f of 4 is equal to -2, like such. And the last part, we'll see that h of 4 would be equal to f of 8. But again, the domain of f does not go out that far, so this would be undefined. And so we know where everything goes now. Where is this? So this point 2, 2, so I'll highlight these in green. So that green one, 2, 2, well, let's see. That would be this point right here. And hey, wait a minute. We don't know where that goes on h. So actually, we'll hold on to that one. Let's see. This point, let me undo that. Sorry about that. So we know that h of 0 is still 0. That's okay. We also know that h of 2 is -2. So I'm going to take this point and plot it right here. The question is, where did that come from? Well, remember, this came from f of, I'm going to do this in yellow, sorry. This came from f of 4, and so this point was actually this 4, -2 that got, again, its x coordinate was cut in half, so that's why it's now at 2, -2. Okay, we're still missing these 2 points right here about where they go, but here's how we could check. If I have, so I know that f of 2 is equal to 2. So that'd be saying the same as 2 times 1. And this 1 right here, that would be the x for h of x would be h of 1 would be equal to f of 2. And so that's going to be 2. And likewise, f of negative 2, which is negative 2, that's going to be equal to h of negative 1. So this negative 2, negative 1, or sorry, negative 2, negative 2 becomes negative 1, negative 2, which is where that is. So let's clean this up now. And likewise, this 2, 2 becomes 1, 2. And so your new graph for h of x, this purple one, and I don't know if that helped. In class today I kind of was starting with this explanation, and then kind of it fell apart. I don't know if you're the judge as to whether this explanation right here fell apart or not. I think it came out a little bit better, but hopefully that kind of explains, helps you see how the input, multiplying that x by 2, effectively squishes the graph inward.